Yeah, welcome. Thanks for the nice introduction. So today we are really going to talk about session tickets. If this title sounds familiar to you, this is because there has already been a blog post by Filippo Valsorda back in 2017 that we need to talk about session tickets. In this blog post, he lists 3 flaws that affect session tickets in TLS and mentions how they are fixed in TLS 1.3. But this is already getting a bit ahead of ourselves. So we really need to talk about session tickets. This title has 3 points that might not be clear to you. First of all, who is we? Then what are session tickets? And then why do we need to talk about them? So let's start with the we. We are researchers from from Paderborn University and Ruhr-Universität Bochum. I'm Sven Hebrok, as introduced. This was started as a master thesis from Simon Nachtigall and then was made into a publication as Usenix this year, together with Marcel, Nurullah, Robert, Juraj, and Jörg. So many of them are also here. So that mostly covers the we. Then we want to talk about session tickets. But the title is missing a minor detail, it's TLS session tickets. And before we talk about session tickets, we need to look into TLS and how TLS works. So, as hopefully most of you know, TLS is this protocol you use on the internet when you browse a website that it encrypts your traffic so that attackers can't steal your data and cannot modify the data. So you visit the RuhrSec website and you see this HTTPS, you see a log in there, and then you're really visiting the RuhrSec website. How does this work on the protocol level? You as a client connect to the server, and to protect the communication you need to establish some keys. This is done in a handshake where you establish a master secret which then both parties have. Using this master secret you can then derive actual keys to encrypt your data and exchange the application data. So then you visit the RuhrSec website, see the program and are happy about it, you know which talks are coming, you close the website. A few minutes later, you want to visit the website again, and you again have to do a handshake, and then only can view the website to know which talks are coming because you just forgot in those few minutes. However, doing the second handshake takes some time. And why would you do another handshake? It would be nice if we could somehow get rid of that. But why does it take time? So the handshake in TLS consists of several messages. As a client, you first send a hello message. You tell to the server, yeah, I want to talk TLS, and the server says, okay, we can talk TLS. To establish the key, first the server needs to send certificates proving, okay, I'm really RuhrSec.com.de, and then they can send you a key exchange message. Then the server's done with that and sends a hello done. You also just send a key exchange message, and only then both parties can establish a key from which you can derive the session keys. And then you can finally exchange application data. However, there's some public key crypto in there which is rather slow and computationally expensive. Namely the key exchange, which contains Diffie-Hellman shares, which you have to compute, you have to do exponentiation operations, so your CPU isn't too happy about them. Further, there are also signatures, so each certificate is signed, which has an RSA or DSS signature in there, and also the key exchange is signed, so you also have to validate that. That's all computational time that you don't want to spend on each connection. So TLS session tickets are there to get rid of this. So we want to get rid of the key exchange, but if we don't have a key exchange, we don't have any keys established anymore. So which keys could we use? As we've already communicated in the past, we can reuse the previous master secret. So we reuse the previous master secret and then can derive new session keys from this. However, how would we do that? The client, okay, they can store the master secret. They have a local disk, they can store it. The server could do so too, but that's expensive. If you have multiple servers, you need to synchronize that state, and that gets a whole mess that server operators don't want to think about. So the idea is that we instead outsource the storage to the client. For this, the server takes the master secret and stores it in a ticket, which they send to the client. The client then stores also this, so the client has to store 2 things, and then upon resumption, they include the ticket and send it back to the server. So that's how the high-level idea. However, writing the master secret directly into a ticket and sending it in plain text isn't a good idea. So this needs to be protected. So we need some way to take the master secret plus something to get the ticket, and the ticket plus something to get the master secret back out again. And this is done using another key, which only the server knows. So on a high level, the ticket consists of the master secret encrypted under a key known to the server, the session ticket encryption key. And the nice thing for the server is that they only have to store the session ticket encryption key. The client, however, needs to store the master secret and the ticket. However, if they don't wish to ever resume the session, they can also delete the master secret and the ticket and later do a full handshake again. So the client has both options, and the server just needs to store one key. Is this done in practice? It is, so nearly all browsers support this because it's a speed up, and browsers like speed ups. And also servers like this, so in our scans we found that nearly 75% of servers support it. Depending on what you scan for, you can find more servers or less servers, but around 75% was the average. As for performance, I said, yeah, public key crypto operations are expensive. How expensive? Cloudflare measured this from the client side and measured that the connection establishment is twice as fast and the CPU time is drastically reduced. So this overall sounds like a nice idea. However, if we come back to this talk, or back to the blog post from Valsorda, we need to talk about session tickets. So seemingly there are flaws inside session tickets. If we take a look at the handshake again, 3 issues are raised by Valsorda, or pointed out. First of all, if we record the session, so if we record the resumption, we can later decrypt it. This is because we don't have another handshake anymore, and just the secret from the ticket is used. So if we have an attacker who has the stake and recorded the communication earlier, they can decrypt the ticket, get the master secret out of it, and can then decrypt the application data. This breaks forward secrecy, so attackers shouldn't be able to record previous communications if they later get long-term keys. Another issue is that the same secret is reused, so because the attacker now has the stake, the ticket, and the master secret from the second session, they also have the master secret for the first session, so they can also decrypt the first session. And the last nail in the coffin that Valsorda mentions is that the tickets are sent in plain text. So as they already contain the master secret of the first session, we don't even need a resumption. So this attacker in TLS 1.2 can already decrypt the first session. So session tickets have some flaws in them, if the stake is ever leaked. So to summarize what session tickets are, we can speed the handshake up with them because we get rid of the key exchange and don't verify the certificate anymore. And they're encrypted using a stake which is only known to the server. But if the stake ever gets leaked, that's an issue. That's a big issue, because we can passively decrypt the traffic, we can decrypt previous and future communications because the master secret is always reused, and something that wasn't mentioned is that you can also actively impersonate the server. So if you're an active attacker, you can also intercept all traffic. But stakes would be chosen securely, right? Given that we have a Usenix paper now, should tell you that stakes aren't chosen securely. So all of this started with a CVE back in 2020, where GNU TLS used incorrect cryptography for encrypting session tickets. Incorrect cryptography in this case means, yeah, choosing a 0 key maybe isn't a good idea. So a common thing once you hear about a bug, you might think, okay, how widespread is this? How many people are affected with this? So how do we find this out? Of course, we know, okay, GNU TLS is affected. We could take a look at all the open source implementations, but we don't know who uses them. So we need to scan servers in the wild. So that's what we want to do. We go to a server, connect to them, and get back a session ticket. That's nice. Then we take a look at RuhrSec, and we see some binary blob. How do we test whether this is encrypted with the 0 key? So, okay, the idea is we decrypt it with a 0 key, and then if some meaningful plain text falls out, seemingly this was encrypted with a 0 key. But how do we even decrypt this? Because we don't know where the initialization vector is, we don't know where the ciphertext is, we don't know what else is in there. So we have to take a step back and take a look at how do session tickets actually work. So on a high level, I said, okay, tickets are just the master secret encrypted. In reality, we have a whole RFC describing how session tickets work. The RFC says, okay, this binary blob consists of some fields where also the master secret is included. So first of all, we have the encrypted state, which includes the master secret, but also some additional state information, which is encrypted using AES 128 CBC. Because it's CBC, we also need an IV, and the RFC also put a length field in there. Next, we have a MAC that is HMAC SHA-256, which is used in an encrypted MAC scheme to protect the ticket against any variations from an attacker. And last, the RFC also mentions that you should regularly change your stack. Because if the stack is leaked, all of your previous communications could be decrypted. So they say, okay, rotate it regularly, because if you, for example, rotate it every day, then you can be sure that, okay, even if it is leaked, only the communication of the last day is affected and not all communications, which is better, but still not good. But that's the recommendation. However, yeah, it's a recommendation, it's no must. So we don't know what implementations actually do. They could reorder all of the fields, they could use completely different crypto. So before we can actually scan the servers, we have to take another step back and take a look at the open source implementations out there. So our plan was to first analyze them, take a look at the ticket format that they use, and take a look at the algorithms that they use. Because AES-CBC was recommended, but it's not mandatory. And then we can also look, while we are looking at the source, look for immediate issues. And after that, we can finally scan. So we have taken a look at open source implementations. The RFC recommends AES-CBC and HMAC SHA-256. As you can see, Boring SSL actually uses these algorithms. In total, we've analyzed 9 libraries and 3 web servers, and taken a look at the algorithms first. 3 implementations actually use exactly the recommendation, while 3 others chose AES-256 CBC, but that's an improvement actually, so that's nice. We also see some complexity in there, so some libraries choose to support multiple algorithms, and Matrix SSL even supporting or using different algorithms depending on the TLS version that is used. This isn't an issue per se, but complexity usually isn't your friend if you talk about security. Another thing that came up is that other schemes used GCM or Charger20, which use smaller initialization vectors, or in their case is nonces, which means it is more likely that key wear out occurs, so they should rotate that key more regularly. However, one thing we noticed is that Botan actually addresses this by introducing another field in their session tickets. So at least some people thought about this. And the one that stands out is GNU TLS, which, while they chose AES-256 CBC, which is stronger than the recommendation, they choose HMAC SHA-1, which is weaker than the recommendation. This isn't broken in any way, but it's still weaker than recommended. So this stood a bit out, but overall, it's not too bad. Then next we looked at the format. This is the one that the RFC recommends. And then we took a look, how do open source implementations handle this? We've seen that only 2 implementations include the length field, but this is fine. In TLS, you have another length field in front of the ticket, so you already know how long the ticket in total is. And because you have only 1 variable length field in there, you also know, okay, the length of that field, you can deduct that. So that is needed, that's redundant. We've seen that 5 libraries use different algorithms, so they used a smaller nonce, shorter nonce. Instead of a 60-byte IV, only 12 bytes, but that's due to the algorithm choice. 3 libraries chose a shorter key name or to omit it, but that's also no issue, because as soon as you verify the MAC, you notice, and your key is a different one, you notice that the MAC doesn't match anymore and you reject the ticket. And Botan was the only one that introduced new fields. First a magic field to just identify their own tickets, and then a seed to counteract the key wear out issue. So they have 16 bytes of additional randomness in there. So all the open source analysts showed that while there are some oddities, there aren't issues. But we have seen that standard algorithms are used, which is nice, but we've also seen that a variation of them are used. So if we want to do our scanning, we have to take a look at various algorithms. For the format, we've also seen it's close to the recommended format. Some fields are longer or shorter. Botan included additional fields, but overall, all used an IV or nonce in front of the ciphertext, and all used an encrypted MAC scheme. So overall, this seems okay. So now we can finally go scanning. But again, before we can scan, we need to know what do we scan. What pitfalls do we evaluate, how do we get tickets, and how do we analyze them afterwards. And then we can finally scan and evaluate the results out of the scan. So, as for potential pitfalls. The first issue that could occur is that you don't encrypt your tickets at all. Well, this may sound arbitrary. We've seen in the past that some email extensions didn't encrypt the emails even though they wanted to, so stuff like that can happen. And also interesting is that such tickets would still work. No error would show up, you would still get a session resumption because the client gets the ticket, stores it, and sends it back to the server later, who can then get the master secret out of it by just reading it. So those would still work, they would fail silently. Next, okay, maybe they have encrypted it, but have chosen a zero key like we've seen in the CVE. So we have to check for that. But also 0 isn't the only key we would consider weak, but also a key like 1, 2, 3, 4, 5 isn't also a bad choice. So we've included further keys. And while we're at it, maybe also we find an implementation that uses an old algorithm like DES. So we've also extended it there. We've also checked for reused keystream, because this can also happen. We've seen countermod or GCM in the list of algorithms that are used. So if you reuse your nonce there, it's possible that the keystream that is generated by that block cipher mode is reused. So in that case, you could also recover the keystream and then decrypt tickets again. And last, we've checked for authentication issues. So first of all, we induced some bit flips into the ticket and checked whether the server still accepts them or behaves differently. Because in that case, that would mean that the encrypt then max scheme doesn't work properly when validating the ticket. And we've also checked for CBC padding oracle issues, which are a special case where you could also get the contents of the ticket without knowing the key. And those have also re-emerged over and over in the last years. We can split these pitfalls into two categories. First, the offline ones, where you just need the ticket and then can throw some CPU power at it offline and analyze the ticket. And the online ones, where we actually have to modify the ticket, send it to the server, and observe the behavior. So now we can finally start. We connect to the server, get a ticket back, and want to check whether it's encrypted or not. But we still have a binary blob. What are we searching for? As we just connected to the server, we have performed a handshake, and both parties have a master secret. So as we know the master secret, and it should be somewhere contained in the ticket, and if it's in plain text in there, we can just search for it. So we search for that binary blob, and if we find that master secret in there, we know it's not encrypted. Okay, that check is doable. But now, if the ticket is actually encrypted, what do we check for? We can't search for the master secret. We can't also encrypt the master secret and check for that ciphertext, because also how would we encrypt it? So our game plan is to first decrypt the session ticket and then check for this master secret in the plain text. However, the main issue here is that we don't know the algorithm, we don't know which key is used, we don't know where the IV is in there, and we don't know where the ciphertext is. So overall, the structure is unknown to us. So we just have a binary blob, and what do? We guess. We guess maybe the IV is in the front, and after that there is immediately the ciphertext, also one byte to the right, or another byte to the right, or maybe also there's the length field in between, so we have to do some guessing. Similarly, we also don't know which algorithm is used. It could be AES in some different mode, it could be Charger, it could be DES, it could be triple DES. And we still also don't know which key to check. So all of this sounds like a lot of combinations which we want to brute force. And this is what we did. We tested TLS-related encryption algorithms, so DS, triple DES, AES, Charger 20 in different modes. For those modes that authenticate the ciphertext, we ignore the authentication tag, because we don't care about that, we just care about the plain text. We also did a similar thing for the authentication algorithms. While this doesn't break session tickets per se, still that would be a weak key. So we also tested for that. In total, we tested 144 potential keys, which were chosen by educated guesses, but also from examples in practice. Like we've seen a recent Hyundai hack where they used the AES keys from the NIST standard with the example keys. We've included that. And overall also keys like 0, 1, 2, 3, 4, 5. So just try it and check what falls out. And in total, because we didn't know the format, we also had to check like over 400 formats, and all of this explodes into many hours of CPU time where we just brute force on tickets, but in the end, seemingly it paid out. So what we do in practice is for the passive scans, we connect to the server multiple times, get a ticket, and store that for later, as well as the master secret and all TLS secrets associated with that. So we do this 10 times for TLS 1.3, 10 times for TLS 1.2, and so on for all versions that are supported, down to TLS 1.0, because SSL didn't support session tickets. For the active scans, yeah, we cannot just collect the tickets, but we also have to connect to the server, get a ticket, modify it, and send it back, and then we have to observe the behavior of the server. So now we know how to scan. So the first scans we did back in the master thesis of Simon used the Trunco list, so our goal was to scan the whole Trunco 1 million list. But before we could do that, we did some test scans to check whether our tool works, which we called then the pre-T1M scans, which just check the 100,000 first hosts on that list. We used those lists and put them into TLS crawler, which is a product of the TLS attacker family, and then used the online tests, so our padding oracle test, to get some results, so in these early versions. And we also checked, then stored the tickets for later and checked them using the offline tests. We also then later did more online tests and more offline tests for a smaller subset of the Trunco list and also for random IP hosts. This mixture gives us popular implementations from the Trunco top 100,000 hosts, but also random smaller TLS implementations from randomly sampled IP hosts. And the last set of scans we performed were the IP full scans, where we scanned the whole IPv4 range for the offline tests. So we connected to all IPv4 hosts using ZMap, checked whether port 443 is open, used zgrep to get tickets, and then analyzed them offline. So let's get to the results. In our first scan, which was, we didn't want to publish it at first, but then, well, we got a result. So we did a Trunco 100,000 host scan and found that 1.9% of hosts were vulnerable. They used a zero stack. This was mostly due to the internet consisting mostly of AWS servers, and AWS had some flaw in there. So again, we've seen a stack that just consists of zeros. We reported this back in April 21, and the flaw was fixed, rather fixed. According to AWS, this might have been introduced back in September 2020, so this has gone unnoticed for maybe half a year, maybe longer, maybe not. We don't know, they don't know, because how would you know if these bugs happen silently? And the probable cause is that Nginx changed the memory format internally, and because some library didn't know of that, it could be that they've written the memory wrong. So these bugs can happen in the wild, and they go unnoticed for a while. As for our other results, let's start with the unencrypted tickets. That's good. We didn't find a single unencrypted ticket, so that's nice. At least everyone is trying to do crypto. We've seen in our full IPv4 scan that we've done only found one reused keystream, but that's one too many. So for that server, we could decrypt the session ticket, get the master secret back out, and then, well, we could have attacked people if we had a man in the middle position. The good news is that we didn't find any servers that had missing authentication protection or were vulnerable to padding oracle attacks, even though those come up every now and again. So this is a good development. And last, for our weak stacks, in the following smaller scans, we found, again, some hosts that we've known from before, from the pre-scans. But in our full IP scan, we found further hosts. And they also had some interesting keys. Before we just found zero keys. There we found more interesting keys. So let's go over those. So the first ones we found were the zero keys, where we just found the key for AES, but didn't find any authentication keys. This was mostly AWS, but also some smaller providers. But we've seen that already. Then we found others where we found the AES key and the HMAC key. Okay. Still a zero key, still standard algorithms. And then we found few implementations that also use a zero key with SHA-348, which we didn't see in an open source implementation, so we don't know where that comes from. So seemingly someone reconfigured the server, but also used the rekey. So that's interesting to see. But we've also seen more interesting keys. So for 3 servers, we've observed, okay, they have an AES key that just counts up from hex 10 to hex 1F, and then the HMAC key also continues to count up. The 0 bytes in the end aren't too interesting because, if you use SHA-256 with a 16-byte key, that key gets padded with zeros in the end. We then connected to the server again and took a look at the ticket, and because we know usually the key name is in the front, we've taken a look at that, and that has 0 starting and then counts up all the way to 2F if you include the HMAC key. Looking at the server headers, we saw that was an Nginx server, and Nginx is exactly configured like that. So you take a file which just has 48 bytes of some data in there, and then it uses passes this as a key name, AES key, and HMAC key. So seemingly this file was just configured to contain bytes that count up. So an interesting configuration flaw. And the last set of servers we found had also an interesting key that was half filled with ASCII1 and half filled with zeros. We don't know how that ended up, but also this seems like it was initialized only to the half, and the other half was uninitialized, and the half that was initialized, that isn't a good value. We don't need to talk about it. But this also suggests that we might have missed keys that were only partially initialized. We didn't test for keys where only 1 or 2 bytes were initialized, because again, that would be a lot of keys. But those could be out there. So in summary of our results, we've seen no authentication issues, which is good. We've seen 1 reused key stream that shouldn't happen, and we've seen a lot of bad keys. Many 0 keys, a few counting keys, and a few that are only partially initialized. So where does this leave us? So in TLS, to come back to our handshake in TLS 1.2, Valsorda raised 3 issues. He said that, yeah, we can decrypt sessions, we can decrypt the first session, and we don't even need to resumption. So they also said that TLS 1.3 fixes that, because TLS 1.3 is nice, right? So regarding the decrypted, that we can decrypt recorded sessions, TLS 1.3 again allows us to do a handshake with a key exchange. This is optional, but if you do it, you can be sure that you get different secrets in there. Similarly, the same secrets aren't reused, even if you don't use the handshake. Then other secrets are derived, and also other secrets are stored in a ticket. And the last issue, that the tickets are sent in plain text, is also fixed by just moving them a bit later into the handshake, where you actually use the session keys to also protect the ticket that is sent. So TLS 1.3 seems fine, right? So even that we now have the stakes, TLS 1.3 servers should be secure. Unfortunately, that's not the case, because we really need to talk about this issue. So if you have an attacker that has the stack again, if there is no key exchange, you can still decrypt the application data, because you have the key from the ticket, there's no key exchange done, so these are all deterministic computations that you can do on your own. If a key exchange is done, the TLS 1.3 still introduced a new concept of zero RTT data, which are only protected using the secret from the ticket. So again, if you have the ticket, you can decrypt the zero RTT data, which are already application data, so this could already be your HTTP traffic. Then what's also possible is you can impersonate the server. Because the certificate isn't checked anymore, and also not in the key exchange, you can still impersonate the server if you are an active person in the middle attacker. So this was possible in 1.2, and it's still possible for the resumption 1.3. So that's still an issue. And even if we would fix all of these issues in 1.4 maybe, we still have to face the fact that even TLS 1.2 is still widely used. So even if we have a secure version 1.3 and have fixed some issues, 1.2 is still widely used. So to summarize all of this, we have seen that 0 maybe isn't a secure key. We've seen that tickets, if they're used incorrectly, can severely undermine the TLS security guarantees. Because usually, if you use TLS, you should be sure that an attacker cannot impersonate the server. You should be sure that if the communication is recorded and you do a Diffie-Hellman key exchange, that later it cannot be decrypted anymore. So to conclude, we have seen that there's a hidden danger in a lot of stuff. So in crypto shortcuts, because we are removing the certificate, suddenly we cannot verify the authenticity of the other party anymore. We cannot be sure that we're really talking to that server. We've seen that the crypto breaks silently because even if the ticket mechanism breaks, even if the key is weak, we cannot see that. This breaks silently and no one will notice for a while. And it's not verifiable easily. Of course, we now have verified it for some servers, but it's only we've seen where it is broken. But you haven't said, okay, there it is secure, because we couldn't check for all keys. That would be very exhaustive. So if you want to take something for this, if you design a protocol, make it verifiable for both parties. Don't make it that the server chooses a key, and you have to trust the server in that it is a secure key. Because otherwise, if you offer people to choose a weak key, someone will do it. That's just how it happens in the wild. If you implement something, it depends on depth. So if some user comes along and says, yeah, I have a key for you, this is all zeros, maybe reject that key. And also, similarly for the reused key stream that was due to a reused nonce, if you see that in your implementation, if a user comes to you and says, I have a nonce, and I want to encrypt another ciphertext, and I have the same nonce again, maybe also reject that. So for your implementations, check what parameters you are given. So I hope that you do this in your implementations and your protocol designs, and I'm happy to take questions.